Okay, so in this video we'll be talking about optimization and how that is related to differentiation. Okay, many real-world situations and a lot of the problems that we'll see in this section require us to find a maximum or minimum point. Okay, we're often asked to find the optimum solution. What's the best? What's the worst? Okay, most of the time it's the best. What's the best possible solution to a problem? Okay, so we're looking for efficiency here when we do these optimization problems. Okay, and let's just do a little bit of review. How do you find a maximum or minimum point? Okay, we know how to do this on a curve, right? We take the derivative and we find the turning points, right? So we can use the first derivative and set it equal to 0. And then finding the zeros of that first derivative will give us the points at which we have possible maximum or minimum points. Okay, remember that just because the derivative is 0, it does not mean that it's automatically going to give us a maximum or minimum. It could also give us a stationary point of inflection. Okay, so there's several ways you can do this. Using differentiation, you could do that. You could do it analytically if you had a nice parabola. Okay, but these are pretty limited here, and you won't always have a calculator. So you could do it by graphing the function by using, for instance, the vertex on a parabola, x equals minus b over 2a. You could use that formula, but probably the most useful one will be, and most powerful will be using differential calculus. Okay? So just remember we can find our first derivative and set it equal to 0. And we could actually use the sign diagram as well. Remember? That's how we determine if it's a maximum, minimum, or stationary point of inflection. Alright, also you need to keep in mind if you use the first derivative sign diagram that you do need to consider global maxima or global minima depending on how the question is phrased. So if the question is asking us what is the maximum on this interval, okay, then you need to find all possible maxima and minima points, right? So you'd have to look at the endpoints specifically when you are finding a global maximum or a global minimum. Okay, and remember, we can use our sign diagrams. Okay, this is all review really. If I have an increasing interval on this side and a decreasing interval on this side, basically if the derivative is positive on one side of the critical point and negative on the other side, then I know that I have a maximum of f of x. If f prime of x looks like this, has a sign diagram like this, I know that my f of x will have a minimum. Okay? Now, I could, if I've determined the 0, I don't always have to use the sign diagram of f prime of x. What I can do is I can use concavity to tell me, is it a maximum or minimum? I think we briefly talked about this when we did curve sketching. But what we'll do is we'll just take the second derivative. Instead of having to plug in numbers into my f prime of x, I'll just find f double prime of x, okay? And then I just plug in any number because any number, I guess, close to a, okay? Any number close to a is what I mean. Okay, so if close to a or at a actually would be probably best. Sorry. So if you plug in x equals a right into the second derivative and the number turns out to be a negative, then it will be concave down. Since we said if the second derivative is negative, the curve is concave down. Okay, we know that relationship. And so we end up with a maximum at x equals a. This is called the second derivative test. Okay? If f double prime of x is positive, then the curve is concave up, and so we have a minimum at x equals a. Right? And of course, you could do the graphical test, which would be just looking at it, just graphing it on your calculator or sketching it and then looking at the graph. But that would be too easy, right? So we're going to focus mostly on using the sign diagram of f prime of x or using the second derivative test. Okay, let's do an example. Okay, you like my colors here? All right, example 1. I want to make a rectangular dish like this. Some of you may have seen this. Okay, we did this in pre-calculus, and some of you may not have seen this before. Okay, that's all right. I want to make a rectangular dish that looks like this. Okay, basically it's going to be a box, rectangular box that has an open top. But I need to make this dish by cutting out identical size squares from the corners of a flat 25 centimeter by 40 centimeter piece of metal. So let's say this was a piece of metal, okay, and this was, let's say that was 25 by 40 centimeters, okay. I'm going to cut out identical squares from each corner and then fold these pieces so that it looks like this, and probably, you know, use glue or weld these together, these edges together, and I'll get a nice square dish. Probably something that you don't want to use, you know, you might not want to give it to your mom, but just for the purposes of this problem, let's just say it's a dish, okay? If I want the volume of this dish to be maximized, I want the biggest possible volume in this dish. How big do I need to cut my squares? Okay, so how big do each of these squares have to be in order to get a dish or a box that looks like this, where the volume is maximized? So this is where we can use differential calculus. Okay, and there are several steps here to do this. Okay, and this is an outline of how to do optimization problems. Okay, but in essence, what I need to do first is I need to build a function. That's going to be my key step. Okay, and you need to be able to extract the appropriate information here and build a function that relates the two variables that are present in the problem. Okay, so I'm going to need to think about what variables I'm interested in. What am I maximizing? That's usually the variable that I want. You know, when I have, like, for instance, dv dx. Okay, usually if this variable is on top, I want my function to be v as a function of x. Okay, so this is usually my independent, right? We talked about this, and this is my dependent. Okay, so I want this to be the form of my function, and I want this to be only x's, or whatever my independent variable is. I want it to be all in terms of this one variable. Okay, so the first thing you want to do is you want to create a diagram, understand what's happening, right, and then build a function. This is probably the hardest step here. Okay, this is the key step here in doing these problems. After that, you should know how to do everything. Once I build my function, I'm going to find the zeros of the first derivative, so I need to derive it, make it. Once I have v of x, you know, then I make it look like, take the derivative, so dv dx or v prime of x. Find the zeros, okay, set it equal to 0. Find where those zeros occur. And then use the tests that we discussed to find the maximum or minimum. What are the tests? We said it was the sign diagram of f prime of x, okay, the sign diagram, or the second derivative test, okay? So those are the two tests that you can use to do this, okay? And this would be if I'm using calculus. I could just, once I have this, graph it, but let's not do that. I want you to practice using f prime of x and f double prime of x. Then you want to answer the question, because this brings us back. You can get lost in the math. This brings you back into the context of the question. Answer the question, preferably in a sentence, okay, so that you're really clear in answering the question. All right, so let's use this procedure to answer this question. All right, so what's step 1? Okay, we know that this box is going to be 25 by 40, and the variable that I'm interested in is the size of the square. Okay, I need to find the size of the square, and since I know both of those sides will be the same, we'll call that x and we'll call that x. Okay, and each square is identical. So then what I can figure out is that this box is going to look like this with these dimensions. Okay, and now the the volume of the box, I can find a relationship for the volume of this box. It will be length times width times height. Okay, so the two variables that I was interested were the size of the squares and then the volume of the box, right? And just write down a bunch of relationships that you think pertain to this, and then oftentimes if you can relate these relationships together, you'll be able to find your function. So that's the process for building a function. Okay. So my volume is length times width times height. My length would be this value, my width would be this value, and my x then would be my height. Okay, my height would be x. And so if I multiply all of that out, I end up with this function. Okay. So this here is my function. It's a volume. Now it's relating the volume of the box relative to the square, which is great. Okay, it's a nice little formula, a calculator per se that tells me the volume of the box. Now it's important here to also talk about domain. Okay, domain helps me keep my answers in perspective. In terms of this question. Okay, so if I restrict my domain, it usually makes my problem a little bit easier to interpret, and it also helps me deal with extraneous solutions or solutions that might be outside of a realistic number. Okay, so try to set your domain once you've built your function. In this case, x, the size of my square, has to be bigger than 0, right? It's got to be a positive square. If I have a negative distance, that's not possible. And also, x must be less than half of 25. How did I get that half of 25? Well, from here to here, that's 25, right? So if the biggest possible square would probably look something like this, okay? And if I go anything bigger than half of 25, I'm going to be overlapping these squares and I'll have nothing, okay? So try to think of your domain. Try to think of the physical restrictions on your domain when you're doing this. Okay, and so x must be a value between 0 and 12.5. 12.5 is half of 25, right? Okay, so now once I've built my function, which is this nice function, I can take the derivative, and I end up with 1000 minus 260x plus 12x squared. I take the derivative and find the zeros, so I factor it all out, set it equal to 0, and my zeros are x equals 50 over 3 or x equals 5. Okay? And once I find my zeros, I think, well, which one am I really interested in, right? So this is where the domain is handy. This 0 turns out to be 16.7, which is outside of my possible domain. If I end up with a square bigger than 16.7, I will end up with a non-existent box. So that doesn't work. Okay? Once I have my 0, I test to see if it's a maximum or minimum. Okay, so I could use two ways. One is to use the sign diagram of f prime of x, or I could use my concavity test or the second derivative test and see the shape of the curve there. Okay, the sign diagram will result in, if I plug in a value that is less than 5, okay, this will become positive because I'll end up with negative times negative. Okay, if I plug in something bigger than 5 and less than 12.5, for instance 10, I will end up with a positive times a negative, and so this will become negative over here. So my sign diagram tells me that it's increasing then decreasing. Okay, my f of x is increasing then decreasing, so I have a maximum here. I could also use concavity. Okay, if I take the second derivative, I end up with this function, and then all I have to do is plug in x equals 5, right? Because at that point, what is the curve going to look like? What's the concavity? And it turns out to be a negative number. If I put in 5 in here, this is bigger than this number, so it'll end up being a negative number, so it's concave down, which means there's a local max there. So the thing about the concavity test is you have a couple extra steps in, I guess, remembering what concave down means and what that means in terms of max or min. So there's a little bit extra interpretation in this process, but it could be less work than this. It's really up to you which one you want to use. And then you answer your question. When 5 centimeter squares are cut out, if the dimensions of the squares are 5 centimeters, the volume is maximized. Okay? So just remember this process here when you are doing these optimization problems.